Hello my dear students, good afternoon. Today we will discuss about phenols. In that first preparations of phenols we will discuss in that Dow process. Dow process is nothing but hydrolysis of chlorobenzene. Hydrolysis of chlorobenzene actually. So chlorobenzene you know already, this one chlorobenzene C6H5Cl when react with sodium hydroxide at 350 degrees Celsius. Okay, in Kelvin if they are asking temperatures are very important. At what temperature this reaction happens, like that they'll ask you, so very important. So what happens, C6H5 OH will form actually, but O minus Na plus actually, first this will form. Okay, so and HCl actually, HCl will go O minus and this. Okay, so now this C6H5ONa, sodium phenoxide we called. What is this? Sodium phenoxide, C6H5O minus Na plus. This when react with HCl, then you will get phenol, C6H5OH. Phenol won't form directly, sodium phenoxide will form first, and then you are getting phenol plus NaCl, this one. Got it? So you know this already. If you have electron withdrawing groups at ortho, meta, ortho, meta and para, then reactivity increases, because chlorine, if you see, it will chlorine, what happens? Chlorine will donate electron pair like this. This pi electron will move towards this. Certainly negative charge you will have at ortho position as well as para position. Do you remember those? So like this you will have C6H5 and double bond Cl plus, and here negative charge. Like that, if these pi electrons are moving downwards, then what happens, you know already. So what happens, sir? So double bond will form here. So I was given this already, just recap, and here you are having Cl plus, and here you have a negative charge. Like that, one more. How these pi electrons if moving upwards, then here pi bond and here negative charge. So from that what you can understand, negative charge you have at ortho and para position. So Cl plus you have. So why I given these resonating structures means, in these resonating structures you can understand ortho and para position you have negative charge, so that at ortho and para, if electron withdrawing groups increases, then reactivity towards NaOH increases. Then what happens? Reactivity increase or decrease? Increases. Electron withdrawing groups increases, then reactivity increase towards what? Towards reaction with sodium hydroxide. So this is very important. So you must know, I told you, if you have NO2 group at ortho, or 3 positions if you have NO2 like that, then you will get picric acid. Do you remember? So in that way you can have more easily that sodium phenoxide and phenol actually. Do you remember? If electron withdrawing groups are at ortho and para, then reactivity what happens? Increases. So these all are very important. This is called Dow process. Dow. Okay. So next we have to discuss second preparation, that is from benzene diazonium chloride. Benzene diazonium chloride. Do you remember what is benzene diazonium chloride? Benzene diazonium chloride means C6H5N2 plus Cl minus. This is called benzene diazonium chloride. How to prepare this? Do you remember? Forgot? C6H5, this one, C6H5NH2 aniline. This when react with NaNO2 plus HCl at 0 to 5 degrees Celsius, then what you will have, do you know? C6H5 and here N2 plus and Cl minus. This is called benzene diazonium. Diazo means two nitrogens. I told you in previous also. Diazonium chloride you will have. Okay, and benzene diazonium chloride is one of the topic for us in nitrogen containing compounds. So there also we will discuss this reaction. So remember, very simple, this nitrogen will add on this, it will become N2, N2 plus, and remaining all NaCl will go and H2 will go and Cl minus, N2 plus and Cl minus you will have. Got it? So this benzene diazonium chloride C6H5 N2 plus and Cl minus, this when react with hydrogen peroxide H2O2 and simple warming, then what happens you can guess. So this will break completely, so that you will have phenol actually now. So C6H5OH phenol. What happens here, understood? This will break completely and N2 plus HCl you will have. Okay, so phenol you have, N2 you have, and HCl you have, like that. Hydrogen peroxide use. Got it? So in this way you can have how benzene diazonium chloride converts to phenol like this. Okay, so two preparations we discussed. One is from chlorobenzene and one is from benzene diazonium chloride. Now preparation of phenol from benzene sulfonic acid. From what? Benzene sulfonic acid actually. Benzene sulfonic acid formula do you know? C6H5SO3H. Do you know? Benzene sulfonation of benzene. C6H6 concentrated H2SO4, then you will get C6H5SO3H. Okay, so what is this? Benzene sulfonic acid. Okay, this one, benzene sulfonic acid. This benzene sulfonic acid, same story, SO3H. When react with same NaOH, then you will get C6H5, SO3H you have, and C6H5 ONA, and this will go, H2SO3 will go out. Okay, C6H5 and O minus Na plus, same. Now this sodium phenoxide we call this. What is this? Sodium phenoxide, C6H5 ONA. So C6H5 ONA, O minus and Na plus. This again will treat with HCl, so that you will get C6H5OH phenol. Phenol plus NaCl you are having. So what here from benzene sulfonic acid, actually these two enough, but you have to understand how benzene sulfonic acid is forming. So benzene when treated with concentrated H2SO4, electrophilic substitution reaction. Do you know this? So SO3 is the electrophile in this. I told no, in sulfonation the electrophile is SO3. So SO3 becomes SO3H. Okay, mechanism also I was given in previous. This benzene sulfonic acid with NaOH, you are having sodium phenoxide. Sodium phenoxide. This sodium phenoxide with HCl, you are getting phenol. This is one more. Okay, so next one, so you have to write, next time saying means you have to write those. Okay, excuse me. Next from cumene. From what? From cumene. Cumene is called isopropyl benzene. So from cumene. Okay, what is cumene means? Isopropyl benzene. Isopropyl benzene. Okay, we use isopropyl benzene, sir. Very important. So first isopropyl benzene, how to prepare I will tell you here. So C6H6 benzene. For this propene I will add. So what is propene? CH3 CH double bond CH2 I am adding. Okay, now what happens, let's see. Propene when I am adding, So like propyl chloride like that. So if I am adding this one, this will come over here. This carbon gets positive charge. If these 5 electrons migrating over here, so this carbon gets what charge? Negative charge. And these 5 electrons migrate towards this carbon only, because here positive charge is more stable, because secondary carbocation is more stable. Do you know that? Okay, so now what happens? This migrates so that you will have here negative charge and here positive charge. Remember that. So now you have like this C6H5, and at this particular carbon, this carbon will add, because this is positive carbon and this is negative carbon. Understanding? These 5 electrons if migrate, here negative charge, here positive charge, and these 5 electrons migrate, here positive charge. So this positive carbon on this. So you will have like this C and H and CH3, and this is CH2 minus. This CH2 minus, and here you have 2 bonds, and here you have a positive charge. Got it? So now here you have hydrogen actually. Everywhere you have hydrogen. So here you must get pi bond, right? That's why these sigma electron CH bond must break. This CH bond must break. Certainly this carbon gets negative, this carbon positive, so double bond you will have. So what you have here, see now, C6H5 and pi bond now will form, new pi bond will form, and now CH, and here it is CH3, and this hydrogen will go there, so CH3. What happened? Understood? Look at here one more time. So this carbon was added on this, so here this CH3 and CH2 minus. So on this carbon you have a positive charge. So to form a pi bond, this CH bond must break. So why here also hydrogen is there? No sir. If it broken, bond will form. No, here already positive charge is there. Here you should generate charge. So to generate charge here, you must break this CH bond. Certainly when this CH bond broken, here negative charge, because H plus will go. So C minus, here C plus, new pi bond here, and this hydrogen will go there, that's why CH3. This is called cumene. What is called? Cumene. Otherwise this is also called isopropyl. See, this is called isopropyl group or not? This middle carbon you have, second CH3 you have. So isopropyl benzene you have. What is this? Isopropyl benzene. Isopropyl benzene is called what? Cumene. Got it, sir, clearly? Okay. Now let's see what happened. So see, our preparation is actually phenol. Our preparation is what? What we are preparing? Phenol. So you got cumene. From cumene you will get Mr. Phenol. How means I will tell you. So C6H5 here, CH you have, and CH3, and here you have CH3 like this. I am writing like this just for understanding. This one and this one both are same. See, 2 methyl groups and CH. Now I am adding O2, oxygen I am adding. Peroxycumene you will have. Very simple. This O2 will insert between this CH. Now what you have? See, C6H5, and here you have a pi bond like this, and C and CH3, and here you have CH3 and OH. Simple way I will tell you, no need of mechanism, very simple. What happens means this will come over here. Now this pi bond will go there. Sorry, this sigma bond will go there. So what happened? OH will come over here. Understanding? So here next step is this one. C6 means this OH group will be here. So OH, phenol. And now this sigma bond transferred here. So C double bond will be. So now this bond will break actually. Understanding? Certainly what happens, you have another byproduct CH3C, CH3 double bond, acetone you are having. What you are having? CH3C double bond O, CH3 acetone, and you have this phenol like this. So this OH group here and this sigma bond is breaking, so C double bond O. Certainly when double bond forming, here this bond will break. Certainly this will become neutral or not, coming over here. Understanding? So lone pair is coming over here. So this bond is breaking. Certainly here lone pair after donation also, that will be cancelled, the positive charge, due to migration of this OO bond or due to breaking of this OO bond. Okay, simple way, remember, this bond will break, OH will be here, this will go there, CH3 C double bond O, CH3 acetone you are having and phenol you are having. So this is one of the important preparation from cumene. Cumene with O2 you are getting peroxycumene, this is called. What is this? Peroxycumene. Peroxycumene converted to phenol, phenol and acetone. Here if you want, you write down name also. What is this? Peroxycumene. Okay, so this is about the preparation. So we had 4 preparations till now. One is from chlorobenzene, one is from benzene diazonium chloride, and one is from benzene sulfonic acid, and one is from cumene, and last and final, that is decking process. Decking process. This is actually substituted phenols you will have, actually substituted, or like this catechol, resorcinol, like that you will have. No, suppose you are having CHO here and here you have OH, and selectively here the CHO will convert into OH actually direct. So for that what we have to do is H2O2 we have to use, and NaOH, and hydrolysis H3O plus we have to use. And now what happens, this C6H5, this is called actually salicylaldehyde, C6H5 OH CHO. Now what happens, this pi bond, okay, so here it will become OH and here it will become OH. Okay, so catechol, and along with that, that oxygen, the CO will go as in the form of CO2 like that. Okay, so catechol you are having. So even you have some amino group here, C6H5, and here you have OH, and CHO you have here. Selectively CHO will convert to OH, means this bond will break, and here you have NH2. Then also same story, here what happened, instead of CHO you are getting OH, that's it. Here what you have OH, that remains here also, NH2 here, so here also NH2 you have, that's it. So these are the preparations of what? Phenols. So how many preparations we had? 5. Yes, 5 preparations we had. Now preparations over. Next we have to discuss about acidic character of phenols actually. This we have to discuss. Very simple, only 5 preparations for phenols. So phenols, if you see, C6H5, and here you have OH, this is phenol. Phenols due to resonance. In phenols resonance takes place or not? So lone pair is there. This lone pair can come over here and this pi bond can come over here. So what happens there? C6H5 and here OH and positive charge actually, and here negative charge actually, phenol, and here you have a double bond. Correct, sir? See, I told you many times, this benzene ring is electron withdrawing group actually. When electron withdrawing group attached, certainly on oxygen electron density decreases. Remember, from oxygen, if electrons are moving away, if electrons are moving away from oxygen, certainly on oxygen electron density decreases. Certainly this sigma bond can migrate towards oxygen. Then H plus can easily come out. Remember this important note. When electrons are moving away from oxygen, so somebody is withdrawing electrons from oxygen, certainly oxygen can lose H plus. Certainly acidic character increases. This is a very important thing. But if reverse happen, I told you alcohols, alkyl groups are electron donating groups. What they will do, alkyl groups, if you see the CH3, CH2, OH, if you see, actually from oxygen, if electrons moving towards the group, then H plus can go easily. But here, this alkyl group is donating electron because this is plus I group. Certainly oxygen have more electron density because these sigma bond electrons are moving towards oxygen. So that this sigma bond migration towards oxygen is difficult because electron repulsions. So H plus cannot come out easily here. Got it what I am saying? So alcohols, phenols, if you compare, phenols are more acidic. Who are more acidic? Phenols are more acidic. Why alcohols are less acidic? Because in alcohols, alkyl group is electron donating group. So electrons are moving towards oxygen. But here electrons are moving away from oxygen. If electrons are moving away from oxygen, then acidic character increases. This is the clarity about alcohols and phenols. So one conclusion I was given right now. What is that conclusion? Phenols are more acidic than alcohols. You remember, alcohols are less acidic even than water, I told you. Told or not? So here I am telling phenols are more acidic because of resonance. Lone pair can involve in resonance, so withdrawing electrons towards benzene ring. Certainly on oxygen positive charge generate so that H plus can go. Correct? So next what happens? Those resonating structures only. So these pi electrons if moving over here, then you have like this C6H5 and double bond OH and plus and here negative charge. And one more resonating structure. If these pi electrons are moving upwards, because here negative charge is there, here should be positive charge. Correct? So if pi electrons are moving upwards, certainly here one bond and here new pi bond will form. This is the new pi bond. And here you have a negative charge and double bond OH plus. Got it? Next what happens? Very simple. This negative charge will go back towards oxygen. Certainly C6H5 and like this you are having OH. Correct? So again it retains its lone pair like this. So what these are? These three are called resonating structures. That's why phenols, our conclusion, phenols are more acidic than whom? Alcohols. Because electron withdrawing group. So electron withdrawing group is who? Benzene. So that's why that we can answer, that we can explain in another way also. See, phenol when react with sodium like that or sodium hydroxide like that, what happens means C6H5 O minus and Na plus and plus half H2. One hydrogen will remove as half H2. So that why this reaction is somewhat fast, because this formed phenoxide, this is called phenoxide, no? C6H5 and O minus is called phenoxide. This is called what? Phenoxide. This phenoxide can be stabilized by resonance. Same like this. By removing H, you write down the resonating structures. How instead of lone pair, now this negative charge will migrate so that these 5 electrons will migrate. So what I am telling, understanding, this is phenoxide. This phenoxide is stabilized by what process? Resonance. What are the resonance? I am showing here. This is phenoxide. Na is not involved, Na plus, that's it. This sodium phenoxide involved in resonance in a same manner. How? Let's see. C6H5 and double bond O. Why double bond O? Negative charge came over here, so double bond O, and these two pi bonds like this, and here negative charge. Same manner like this, negative charge, same manner or not? But what is the difference in phenol resonating structures and phenoxide resonating structures? In phenol resonating structures, you have double bond OH plus, but here double bond O, that's the difference. So phenoxide can be stable so that it can easily lose H plus or not. That's it. Understanding? So sodium can easily replace this hydrogen. But same sodium reaction with ethanol is slow. Why? Ethanol I shown in previous. Alkyl group is donating electrons. So here phenoxide is stable. But if you see this reaction CH3 and CH2OH with sodium, the reaction is very slow. Why? Because this alkyl group is donating group, and CH3 and CH2O minus Na plus will form, but this is not stable. Understanding? So due to stability of phenoxide ion, that stability is due to what? Due to formation of resonating structures. Phenols are more acidic. So the formed phenoxide ion is more stable. The remaining resonating structures you can write. These 5 electrons, if migrate downwards, certainly again negative charge here, then you will have like this. Double bond O and negative charge here. Correct? Next structure if you want, it's very simple. These 5 electrons upwards, same like this. Upwards. Okay, then you will have structure like this. Double bond here and new pi bond here. I am showing new pi bond, how formed. Here positive and here negative. And here negative charge and double bond. And original structure, it retains negative charge on oxygen. Same like this we will have. Phenoxide ion we will have again. So phenols are more acidic due to these resonating structures. These resonating structures, just for time pass I am writing, you are thinking no. Even electrophilic substitution reactions on phenol I will explain. There I will say on phenol electrophilic substitution reactions takes place at ortho and para I will say. Then you have no right to ask why at ortho para, because in resonating structures I am showing here you have negative charge at ortho, negative charge at para, negative charge again at ortho. So electrophile means positive species. Those positive species can add at either ortho position and para position. So here I am giving you one more important note, that is in phenols the electrophilic substitution reactions takes place at ortho and para. So where you have negative charge, let's see here. In phenols, negative charge you have at ortho and para position. So phenols are more acidic, but one more thing, on phenols if electron withdrawing groups increases, then acidic character what happens? What I am saying, understanding? At ortho, this is ortho or not? This is ortho and this is para, again this is ortho. At ortho and para you have negative charges. So this negative charge can be stabilized by some electron withdrawing groups. Correct or not? Correct or not? Because negative charge, no. Electron withdrawing groups means what? They are deficient. At ortho you have rich, para rich, ortho rich. Electron withdrawing groups means 4. So they can be stabilized at ortho as well as para. So what I am trying to tell you here, if electron withdrawing groups attached at ortho and para, then acidic nature of phenols, what happens? Increases. Suppose if you have this one, C6H5OH and C6H5OH and NO2 and C6H5 and OH NO2 and C6H5 and OH and NO2. So what is NO2? You know this. NO2 is electron withdrawing group. You remember or not? Okay. I was given minus M groups and plus M groups. So NO2 I was given as minus M group. That means electron withdrawing groups. Certainly, who is more acidic among these? This is 1 and this is 2 and this is 3 and this is 4. Who is more acidic means I will write here. Look at here everyone. So who is more acidic means para is oppositely withdrawing. See, actually I said electron withdrawing groups attached at ortho and para, then acidic nature increases in phenols. So ortho NO2, para NO2. Then who is more acidic means I'll tell you. Second one is more acidic than third one. Of course, bit small difference only you are having. And next is 4 and least is 1. However, you have electron withdrawing group, but meta means you don't have any positive charge, any negative charge. That's why it is somewhat less acidic. Sir, understanding everyone? So para, second one, this is para nitrophenol actually. Para nitrophenol is more acidic than orthonitro because some intramolecular hydrogen bonding is there. So H plus cannot go easily. Bit small difference actually. If you want pKa values, I will give. It's 7.1, it's 7.2, it is some 8 point something, 8.2 something, and it is like that only somewhat. Okay, more. So pKa value is less, acidic character is more. Do you remember I was given in previous? Ka value is more, pKa value is less, then acidic character is more I was given. Do you remember this? So for para-nitrophenol, the acidic character is more and its value is 7.1 something, pKa value. Why? Its hydrogen is not involving in any interaction with NO2 because they are far from each other and NO2 withdraws straightly in opposite manner. So this para-nitrophenol slightly more acidic than this. This is somewhat more acidic than even phenol because difference between phenol and meta-nitrophenol is electron withdrawing group. Somewhere at least NO2 is there, electron withdrawing group. But what I said, if electron withdrawing groups are there at ortho and para, then acidic character increases. Here meta is there, then how it is acidic means than these two less acidic, but than phenol, meta-nitrophenol is somewhat acidic because NO2 group is present, electron withdrawing group at least present somewhere, but here no electron withdrawing group. So these are very, very important. So what I said, if electron withdrawing groups increases, then acidic character increases. Okay. If electron withdrawing groups are more present at ortho and para, suppose this one, if you take C6H5, OH, NO2, NO2 is there, and C6H5, OH, and NO2 you have, C6H5, OH, and NO2 you have. Among these three, who is more acidic means pakka this one is more acidic. Why more acidic? There are 3 electron withdrawing groups. So more the withdrawing groups, more will be the acidic character. H plus can go easily. Getting? So more the number of withdrawing groups, more will be the acidic character. Okay, these are very, very important. So this is called picric acid. 1, 2, 3, 4, 5, 6. 2, 4, 6 trinitrophenol, which is called picric acid. But so if electron donating groups increases, then acidic character decreases. If electron donating groups, okay, like alkyl groups, plus I groups are or plus M groups are called electron donating groups or not. Suppose if electron donating group is there, phenol is there, and this one C6H5 and OH CH3 metacresol. Do you remember metacresol? Next C6H5OH CH3 paracresol. This one para, ortho metapara, paracresol and orthocresol. C6H5OH CH3. What CH3 here? CH3 is electron donating group. Electron withdrawing group is there, acidic character is more at all than para. But if electron donating group is there, then these all 3 are less acidic even than phenol. Here phenol is more acidic. Why phenol is more acidic? Actually withdrawing groups, if their acidic character increases, because they will withdraw electrons so that H plus can move. But here methyl group is donating, actually withdrawing required to lose H plus. These electrons must come downwards, but methyl group is donating upwards electrons, so that H plus cannot come out easily. So phenol is more acidic if electron donating groups are there. Understand? So this is the model. That's it. So this is about acidic character. Few more examples I will give you, and this also you must remember, which has more pKa value, like that they'll ask you. So if they ask like that, you must know, okay, which has more pKa means less acidic they are asking. Which is having less pKa value, okay, which is more acidic they are asking. Like that you must have clarity. So please revise all these concepts, and these are very, very important. Acidic character mainly very important, and preparations also. Please revise all those things and write down.